So today we are going to continue on with our discussion of interacting systems. So as a recap, what we did is we defined so this is NVT. This was the configuration integral. This was all of the possible positions of all of the different molecules. So how we wrote it, so if we assume that the total internal energy of a system based on the orientation and position of the particles is only the pairwise additivity of all the binary pairs, right? So if I have particle 1, particle 2, particle 3, 1, 2, 3, the total internal energy of this system, that is from the configuration and orientation of the molecules, not their internal modes like velocity, vibrations, and so on and so forth. The total energy would be the energy associated with the interactions between 1 and 2, plus the interactions with 1 and 3, plus the interactions with 2 and 3, just basically all the possible combinations. Right? This is the pairwise additivity assumption. This is the cornerstone of all basically molecular level calculations. With this approximation, we can write out the configuration integral as a big, nasty integral where we're integrating over all of the volume and all of the positions of every single particle. And then for every single particle, this is a lovely, obnoxious. So we're summing up, we're taking the product summation from particle 1. And then here, this just arithmetic is just to make sure that we're not double counting. So if this is 1, then this is 2 through n. This is 2, this is 3 through n. This is 4, this is 5 through n. And then we repeat this process for every single particle in every single position, and its interaction energy with every other particle for every single position, every single orientation across the whole unit volume. I, for one, certainly don't want to deal with this. Then what we talked about were some interparticle potentials. So in the case of U, R, I, J, this is the energy as a function of the separation distance. So we talked about a couple ones. The hard sphere potential. We had the square well potential. And we had the Leonard-Jones potential. These are all different ones we had discussed. And these are models for how we can represent how particles interact. So instead of us having to develop let's say some sort of arbitrary activity coefficient model, or whatever the case is. Now we've simplified down all of the polydispersity of all the different types of molecules in the universe to how do different particle types, how do different molecule types, how do different atom types interact. And so the discussion is, which is the shape of the potential for how real systems behave? What are the parameters in the potential to best match the properties of different materials? So we would expect something like, so in the case of, let's say, the hard sphere potential, we have some parameter sigma, which roughly corresponds to the radius of a individual particle or atom. Let's say this is, if we were trying to think here, the radius of helium versus the radius of xenon. Which one do we think would be bigger? Xenon. Right? And so hopefully the model would bear that out. I don't know for sure, but I'm pretty confident it does. So what we've done is now we've simplified down a lot of our uncertainty into really fundamental interactions and discussions about the actual physics of how molecules and atoms interact, as opposed to classical thermo, where it was all made up. Right? It wasn't entirely made up, but basically we didn't know how to measure, we didn't know how to calculate any properties with classical thermo. We knew what properties we needed to measure, and once we measured those properties, then we could perform additional calculations. Now we're actually talking about the real underlying physics of what's going on. Whereas in macroscopic thermo, we were just talking about the large-scale macroscopic collective rules that particles had to behave, and we made inferences based on the interaction of those rules. Now we're for real talking about the actual physics of the particles, or at least an approximation of it. So what we didn't finish up with on last lecture that I wanted to run through very quickly here, we can further simplify the configuration integral. Effectively, we can approximate this integral here. I won't go through the math, but in the book it has it. We can come up with this result here. So what ends up happening is to get the configuration integral in this form, we assumed pairwise additivity. To simplify it down over here, we're doing another approximation where we basically approximate this integral and then neglect higher order terms in that approximation. So kind of like a Taylor series approximation. So this is an approximation of an approximation. And what we get here is that we can calculate the configuration integral as a function of this parameter beta, where the beta is effectively equal to some integration on the binary interaction or the intermolecular potential. So if we take this solution, we apply our relationship for the configuration integral to our solution, and what it spits out what is this? What equation did I just write?
Virial.
It's a virial equation of state. So the virial equation of state has its fundamental origins in stat mech. In this case, the second virial coefficient is directly related to this beta coefficient, or beta parameter, rather. What are some shortcomings of the virial equation of state? When is a good time to use it in a classical thermo calculation?
Gas phase only.
Gas phase? Which conditions in gas phase would you expect a little bit better predictions?
Low pressure.
Well, low pressure gas phase is pretty easy to do. I mean, as you get close to sort of like a saturation conditions, that would be better. But could you use this for vapor-liquid equilibrium? Why? What's wrong with the virial equation of state for vapor-liquid equilibrium? This is a warm-up for the final exam.
Doesn't predict the two-phase.
Why doesn't it predict the two phases?
It's not cubic.
Bingo. This is only a quadratic function. So you either have a stable fluid or an unstable fluid. You don't have two stable fluid solutions with the virial equation of state. So all the approximations that go into this, while they do have their origins in fairly solid science, the approximations result in an equation that fails to predict liquid structure. So it's good, it's a step forward. It's certainly a much more rigorous and theoretical model than the equation, sorry, the ideal gas law, but it still fails to predict a lot of the properties. And largely that failure is in this step here, going from here to there. That's where the approximations get a little bit too severe. The pairwise additivity is not the major issue. So what we can do then is we can calculate what the second virial coefficient is for different intermolecular potentials. So I won't show the math, just to move on so we can talk about new material. For the hard sphere, if you evaluate this integral, so effectively we're going to plug in this piecewise function for the the hard sphere potential into this expression here, evaluate it to get to the second virial coefficient. It is a nice and clean expression. In this case, the hard sphere potential, as a reminder, is equal to infinity when your separation distance is less than or equal to your radius, and it is 0 when it is greater than. The reason why we have the hard sphere and square well potentials is because integrating this piecewise is not too bad. Square well. So the square well potential, if we write this one out, is hard sphere at really low separation distances. So it's infinity for the radius of separation less than or equal to the radius. You have some well depth in between the radius and some scaling factor of the radius, and then it is 0 beyond that point. That's the function there. And the second virial coefficient, when you integrate this piecewise, gets to be a much more complicated expression. This function here isn't particularly interesting because it's just a constant. Effectively, this constant represents the excluded volume of the particles themselves. But if we take a look at this second virial coefficient for the square well potential, we're going to find two parameters. This is some kind of a special reduced temperature, not the same as the macroscopic reduced temperature, but we're going to define it as basically the temperature scaled by the attractiveness of that square well. Effectively, how deep is that attractive region for the two particles? And then just for convenience, we're going to scale the virial coefficient based on this factor up front, just to make it easier to see. That's all I'm doing is dividing this over there. So if we look at the function, if we plot out T star, this is 0. It should asymptotically approach 0. And this is, 1. So effectively, with the square well potential at high temperature, right, and what we mean by high temperature, we mean relative to the depth of that square well. How deep is this attractive region? How sticky are the particles is another way to think about that. As you get to lower temperatures, that stickiness starts to be important. But above that, it's basically an ideal gas. So with that being said, this is a sort of another connection that we have between the macroscopic and the microscopic world. That wraps up what we wanted to get done last time. Any questions on that? So with that, let's move on and we'll start to look at this handout that we have in front of us. So I want to give you a little bit of a brief introduction about that handout first. What we have learned so far about how molecules behave is that the two most important things to understand are, one, how does a molecule behave in a vacuum by itself? What is its mass? What are its rotational energy? What's its vibrational energy? What are its electronic energy modes? And so on and so forth. Right? So we can understand the collection of isolated particles, understand their energy, and that's effectively just an ideal gas. So we can develop more and more complex molecules. We talked about ideal monatomic gas and ideal diatomic gas, but we could do exactly the same thing for a polyatomic gas. Just more rotations, more vibrations, all sorts of additional complexity. But those models exist, they're off the shelf, you can grab them. So you can estimate with StatMech what is the heat capacity of heptane. Conceptually, it's no more difficult than with oxygen. It's just a lot more math and a lot more complicated. So that's step one. Step two is we need to know where the molecules are and how the energy or the potential energy changes based on how close or far apart they are. So for non-ideal systems, we have two needs. One, we need molecular positions. And two, we need potential energy functions. Potential energy functions. All right, and these would be our oh my gosh, I'm drawing a blank. What do we call these again? We call these interaction potentials or something like that. So for example, Leonard-Jones, square well, hard sphere. Okay, so we have some models that we've already discussed of these different interaction potentials. What's the potential energy as a function of the separation distance between two particles? And there's lots more of these. The book has additional ones. One of the more important ones that we're not discussing is Coulombic potential, which is basically just electrostatic charges. So if I have water, for example, we're going to have a more electronegative region by the oxygen, and we're going to have a greater electropositive region by the hydrogen. So in addition to having kind of a Leonard-Jones type interaction between the hydrogens, between the oxygens, and between the oxygens and hydrogens, there's also this charge that's going to affect things. And so in a Coulombic potential, it's never attractive, it's always repulsive. Well, in the case of positive, in the case of positive-negative, it's always attractive. So that's an additional really important one that comes up in simulations a lot. But basically, we've got a lot of models for how these interact. But what we haven't talked too much about is how do we actually keep track of molecular positions. So you can cheat a little bit, but I want you guys to say it. What is these little plots in front of you? What are those?
Radial distribution.
Those are radial distribution functions. That is the single most important way to communicate molecular structure. So I can guarantee you, in your life, as a graduate student and as a researcher, the concept of a radial distribution function will come up very frequently. Immensely frequently. To the point where, if when you graduate somebody asks you what a radial distribution function is and you say, I don't know what that is, it will reflect very badly on your defense or at your job interview. So this is a core fundamental concept that you must internalize and just know when someone mentions a radial distribution function, you have to know what that information is trying to convey. So, what we're going to be talking about today and over the next day or so is how do we actually get access to this information of what the structure of a fluid is, what the structure of how the molecules interact are. So we're talking about radial distribution function. Radial distribution function. Oftentimes I'll write RDF. Mathematically, we can write it as G of R. In this case, this would be one-dimensional. Or we can have a three-dimensional function. So conceptually, what this does is it describes So effectively, the radial distribution function tells us the likelihood of finding a particle at some position. Now this could be one-dimensional, in which case it would be the absolute value of the displacement vector. Or in the 3D, you could have it a full 3D or a 2D displacement, away from another particle relative to the bulk density. So very quickly, when we look at those little plots in front of you, that straight line, that is if there's no additional likelihood. That's just your bulk density. So when you have a peak in the radial distribution function, that means that fluids on average are more likely to be found at a separation distance relative to that peak compared to if the fluids are just randomly dispersed throughout the system. So the sharpness of the peaks and the narrowness of the peaks dictate how frequently and how structured that fluid is. So the fewer number of peaks and the broader the peaks, those both indicate a less ordered or structured fluid. So some general properties. As the separation distance goes to 0, the radial distribution function goes to 0. Why? Conceptually.
Because they will particles.
You can't overlap. That's the excluded volume. And as the separation distance goes really large, the radial distribution function goes to 1, and that's because it's normalized. It's normalized to the bulk density. So in other words, we'll be talking a little bit more about mathematically how we calculate this. We're not going to go into too much detail, but enough just so we can get a conceptual understanding. But effectively, if I have a particle this is a radius. Now, analytically, we can call this dr, right, like a differentially thin element, but in practice, we can't. So we have a resolution that we can measure radial distribution functions from, and conversely, when we do scattering experiments, we have a resolution from which we can measure the structure as well. What we're effectively saying is, this is our particle of reference. What is the likelihood of finding another particle inside of this shell that is defined by r plus delta r relative to as if it was a random distribution? So more or less, we're going to count up. So here we're counting up 1, 2, 3 particles. We have 3 particles in a volume shell element. Is that more particles than we would expect just based on the bulk density? Is it fewer particles than we would expect from the bulk density? Or is it about the same? So as your radius gets really, 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 really big, your volume element becomes a macroscopically sized volume element. So on average, we should expect there to be just the same amount of number of particles that we would expect to see based on the bulk density. Conceptually, is this clicking? Does that make sense? So the radial distribution function is the excess number of particles, or excess likelihood of finding a particle, relative to the volume and the number of particles just based on the density. So that tells us that the local density is either higher or lower at different positions. And that fluid structure tells us a lot of information and properties about the fluid itself. Yes?
Why they should be different?
What's that?
Why they should be different? The local density and the bulk density. Why?
Because there's local order in the fluid. On the bulk scale, all of that local structure has been isolated. But if you were to zoom down to, let's say, a square or cubic nanometer, that's maybe even too big, maybe a fraction of a cubic nanometer, and move that around through the box and freeze the molecules in positions, you would have a statistical fluctuation of densities. You would have some regions where there's more molecules than you would expect based on the density, bulk density, and some regions where you have less. Because the fluids are all dynamically moving around. It's not a static pudding like a classical, what's it called, the plum pudding model of matter. So these molecules are dynamically moving around, and how they're dynamically moving around will introduce structure. And that's what we're going to talk about right now. We're going to break down these radial distribution functions. Does that satisfy your question?
Do we expect the same with gases?
Yes, gases will have a radial distribution function as well. It'll be less pronounced than liquids. Liquids are far more interesting to look at. So the top one is the radial distribution function of liquid argon at 91.8 Kelvin. I believe that's close to the boiling point. So this is just a barely condensed liquid. I think so. I have to double check my numbers. We'll talk about how we get this. I've got a demonstration that I'll do probably on Monday where we talk about diffraction and how we can actually measure radial distribution functions from diffraction. But basically, this is X-ray scattering measurements that were made on liquid argon. And then they did a Fourier transform on the diffraction pattern, and that's how you can get the radial distribution function. So the radial distribution function and the diffraction pattern, they also call it the structure factor, those are just Fourier transforms of one another. So you can measure radial distribution functions with scattering, X-ray, neutron, light scattering. If you'll see here, this last name, H. Eyring. Has anyone been in the Henry Eyring Chemistry Building? So this is, and who's heard of the journal Proceedings of the National Academy of Science? Who's heard of that journal? Oh yeah, it's a good journal. So in 1981, this is really, really good research. About 40 years ago. So we're getting, we started off talking about 1600s in the first law, 1800s for the second law. We're getting closer. We're getting to 1980s now. The bottom one here is 2000s, right? So we're getting real close. We're getting close to real modern research now. But anyway, so this was good stuff back in the day. It may seem trite to think about why do we care about the structure of liquid argon, right? But again, it validates how molecules interact, how accurate are our baseline simplifications. And in this, so the solid line is the actual measurements, and the dashed line is some lattice-based theory that they developed for argon itself. And it's not too bad, actually. Okay, so based on what we know about the radial distribution function, and I will try and approximately reproduce it here. Here's 1. Let's see, so we have 4, 6, 8, 10. So we have a peak kind of here, trough about there, smaller peak. I'm not doing super good on this. And 10, and it starts to oscillate. Okay, so let's go through this a little bit. If I were to take this information and I wanted to apply the hard sphere potential, what would I say is an approximate representation of the radius of argon, liquid argon, using this experimentally measured data that I could use to tune my hard sphere model?
4.
4? Four. Don't base. My drawing's bad. Do based on these ones here. What would you say?
3. It's like half of that. Right?
Yeah, the chart kind of drops off, but maybe we would say approximately that. So if I wanted to min-match this here, so this sigma approximately corresponds to the excluded volume. In this case, this is where G of R should go to 0. And so I would say for this particular one here, I would say it's approximately 3.5 angstroms. And so the Sandler book actually has a table of tuned square well potentials. So in table 8.1-1, they have Leonard-Jones parameters. And for argon, they indeed have 3.504. And they also have the attraction, 0.7 Kelvin. So not too bad. So if I were an argon atom, how close on average is the nearest next argon atom?
4.
About 4. Right, we can see here, this is effectively the nearest neighbor. Yes?
Is it like at 3.5 GR is going to 1, not 0?
So this plot doesn't go all the way down to 0, so it's highlighting the interesting features. But it as you go to lower R, this will continue to drop and continue to drop and continue to drop. So it has to go down to 0.
Okay, so we are interested at 0 and not at 1.
At 1, meaning, are you talking about R of 1?
So yeah, the GR.
G of R of 1, if we believe this tuned Leonard-Jones model, should be 0. Because that is significantly smaller than the excluded radius of the argon particle itself. So there should be no likelihood of finding a particle there. But yeah, so the plot doesn't show, but it should drop off to 0. The bottom one does actually show it going all the way down to 0. And you can see it drops off pretty sharply on a lot of these different ones for water. So oftentimes what they also describe is they call these the solvation shell. So we can call this the first, the second, and the third solvation shells. You'll notice that as you get to the higher solvation shells, the intensity or the magnitude of the G of R peak becomes smaller and it becomes wider. Right? So let's think about this for a second. Let's think about this like kind of propagating a chain. Right? I'm an argon particle here. I have a pretty good likelihood of having a nearest neighbor about 4 angstroms away. Okay? So I'm 4 angstroms away. Now I'm this new argon particle. And I want to see how close is my next neighbor over there. Well, my next neighbor is about 4 angstroms away, but all this uncertainty adds up, right? There's a little bit of plus or minus here. There's a little bit of plus or minus here. There's a little bit of plus or minus here. And you can see as you get further and further away, that uncertainty of where the nearest neighbor position is will propagate through, and eventually from me here all the way to the door, like 5 or 6 argons away, it's completely uncorrelated positions. And that's going to be characteristics of a liquid. Now if I were a crystal, it's different, right? If I were a crystal and I have, let's say, a lattice spacing of 4 angstroms as well, if I'm here, I have a very well-defined position here, there's a very well-defined position here, there's a very well-defined position here. So in a crystal, we would expect these to be very sharp, very well-positioned peaks. Now you still will get a drop-off, and that's just because how we calculate it, because as you get to a larger and larger volume element in your radial distribution function calculation, you're just capturing more and more particles, so eventually you will decay down to the bulk value. But for a crystal, you get sharp peak, sharp peak, sharp peak, and the intensity of the peaks and the position of the peaks tell you exactly what the crystal structure is. And I will be very clear, I am terrible at crystallography. So I would say I'm decent at liquid structures. Crystallography, no thank you. There's a lot of history and tools built up there that I don't have access to in my brain. One other thing, if we look at the Leonard-Jones parameters here, so if you look at the Leonard-Jones function, the position here of this potential energy minimum well is at, let's see, R min is equal to 2 to the 1/6 of the radius or sigma property. And so for argon, that's what we're talking about, is 3.93 angstroms. And so if we look at our chart here, I would say 3.93 seems pretty good as the minimum separation distance. So that means most of the argon particles, if the Leonard-Jones model is correct, right, this is just a model, right, most of the argons want to sit in that spot. So if we were to expand it, we would expect it to cool down, as a throwback to the last class. How do we feel about argon? So argon is a monatomic gas, relatively straightforward. Let's talk about water next. Okay, so water, there's a few more features into it. Because water has more atom types. So its structure is more difficult to characterize. So I will, oh boy, I don't know if I want to try and draw this or not. So in water's case, we actually have 3 lines. One, we have the oxygen-oxygen line. Okay, and it's got dots. See if I can find a different colored pen for the other ones. Oh, these lines look like getting crowded. We have oxygen-hydrogen line. Goes up. It's a very sharp peak. You know, I'm not too disappointed in that one, even though you can't see it because it's a faint marker. And then the last one is the hydrogen-hydrogen line, in which case, oh my goodness. Okay, so green is our hydrogen-hydrogen, red is our oxygen-hydrogen, and black is our oxygen-oxygen. So what we're looking at here, we're looking at G alpha beta of R, which are partial radial distribution functions. So for water, we have 3 unique atom types. Hydrogen, oxygen, my bad. So that leads us to 3 combinations, HH, OH, and OO. So if we describe the relative orientations of hydrogen relative to hydrogen, oxygen relative to oxygen, and the cross term, then we fully describe the structure. Okay. First question. What is the oxygen-hydrogen bond distance in water? So based on here, I haven't heard the right answer yet.
1.
It's about 1. How do we know? This peak right here. This is the oxygen-hydrogen radial distribution function. And why is it really, really, really big?
Hydrogen bond.
Because you have it bonded together, you
They're bonded.
have a much higher probability.
So every single oxygen in water will have 2 hydrogens. So the magnitude of this peak is not all that particularly interesting because we already know what water looks like. Let's say we didn't know what water looks like, then we could use this information to figure out how many hydrogens are actually bonded to oxygens. But the peak position is the more interesting part. Okay, next question. What is the hydrogen bond average separation distance in water? This is intermolecular. 1.5. That corresponds to, let's see, no, hydrogen, hydrogen. It corresponds to this one here, right? In water, I'm oxygen. At a certain separation distance, I have an extremely high probability of finding a hydrogen there. That's this massive peak. But beyond that, nothing. So it should drop down virtually to 0. I didn't draw it very well, but in your figure right here, you can see that the OH dashed line goes basically to 0, meaning that there's no other oxygen that close. Then we start to get the peak going up again. In this case, actually, it's a little bit more like maybe like 1.7, 1.8. So that's how close two molecules are together of water in solution. Now, if you look at the hydrogen-hydrogen one, that peak is not quite as sharp. And that's likely because that bond can vibrate and oscillate. So it's not going to necessarily be at a well-defined position. Right? So the hydrogen-hydrogen peak, which is this green one here, isn't all that stellar and impressive. Right? So you can tell that there's some flexibility in the water molecule bond themselves. Now the oxygen-oxygen peak is actually relatively strongly pronounced as well. So that gives us some insight into saying that water is a highly structured fluid, because the only oxygen-oxygen correlation that can exist is intermolecular correlation. And indeed, water is a very structured fluid, right? And that's what makes it such an interesting topic to study. So this particular paper here was out in 2000. So this guy who did this work here, Alan Soper, or Soper, I never quite know how to pronounce his name. Basically, this experiment was performed, this was neutron scattering. So what's unique about neutron scattering that's distinct about X-ray scattering? In this experiment here, X-rays get scattered by electrons. We can't control how many electrons a particle has. If we change the electrons, we change all of its properties. It's a different compound. Unless we look at ionized things, but that's really hard to do. So for something like argon, who cares? Use X-rays, right? Because I can't modify argon. Argon is the way that it is. Water, you can do something really clever with. If we substitute the hydrogen for deuterium, and we assume that doesn't change things too much, it does change things, but not too much. Hydrogen and deuterium scatter neutrons differently. And when we mean neutrons, we mean cold neutrons. Neutrons that have been chilled down to about 5 degrees, 10 degrees Kelvin. When you chill down a particle that's as small as a neutron, which has a very low mass, to a temperature that is very low, what does quantum mechanics tell us is going to happen?
Move slowly.
Well, move slowly, but also it turns into more of a wave. So the wavelength of a neutron at about 5 to 10 Kelvin is on the order of a couple of angstroms, which is kind of amazing, right? Because a neutron is immensely small, right? The nucleus is 0.00001% of the atom volume, and the nucleus is only a fraction of them are neutrons. But when you cool it down enough, its position gets so delocalized that its probability gets spread out to the order of angstroms. X-rays, so if you use like 8 keV electron X-rays, which is pretty common for copper K alpha source, I don't know if these terms sound familiar, that corresponds to about a 1.5 angstrom wavelength as well. So we can get neutrons to behave like waves if we cool them down very, very cold. But the cool thing here then is that if I do a hydrogenated water scattering pattern, a deuterated water scattering pattern, and a mixture of hydrogenated and deuterated water scattering pattern, then that gives me 3 overall structure factors that I can then Fourier transform to give me 3 partial radial distribution functions. So we're going to talk a little bit more about scattering theory as time goes on, but I wanted to kind of introduce how this plot was actually generated. So this tells us all of the information that we need to know about water. Now the cool thing about the radial distribution function is, because it is such a prolific measurement, we have a tremendous number of tools that if we know the radial distribution function of a particle, we can calculate its internal energy, we can calculate its pressure, we can calculate lots of other different properties. So the radial distribution function has been, by all means, adopted as the primary tool of communicating structure in a fluid itself, or a solid in the case of a crystal, or even an amorphous particle itself. So solid, liquid, gas, if you want to communicate how the molecules are organized, radial distribution function is the tool that you use. And now, hopefully everyone, the key thing here is I don't necessarily care that we understand the structure of liquid argon. Structure of water is an important one to understand here. But the main thing I want everyone to walk away with is when you see a radial distribution function, you look at all the squiggles, you can at least say, oh, I kind of get what this is saying. Sharp peaks, highly ordered. Broad peaks, disordered. If it disorders very quickly, flattens out, that means there's not a lot of long-range structure. If you see peaks persisting into long distances, that means there's a lot of long-range structure. But when it comes to liquids and dense fluids, right, it could be non-ideal gases, everything, all of the properties of matter are based on how the molecules are positioned. So if you know the position of molecules relative to one another, you know all of the properties about that fluid, thermodynamically. If you want to know something like diffusivity or viscosity, then we actually have to know how quickly the molecules tumble and rotate around one another. But those are not actually equilibrium properties. Those are kinetic and transport properties. So for thermodynamic properties, all we need is the structure. If we have the structure and how the particles interact, we know everything we need to know about the properties of that fluid. Density, internal energy, enthalpy, Gibbs free energy, etc. Any questions? So over the next couple of days before things wind down, final exam is 1 week from today, believe it or not. So homework, I made it due at midnight on Monday. I'll have office hours tomorrow. But we're going to be talking more about how do we generate representations of fluid structure, either experimentally or computationally. And that's really where we get to cutting-edge modern research in thermodynamics, is the different rules and criteria that we use to predict what the fluid structure is. Because if we can accurately represent the fluid structure, then presumably we can accurately represent the macroscopic structure. And if we have simulation approaches that say, I know how hydrogen and carbon interact, I know how oxygen and carbon interact, then in the computer, I can build any arbitrary molecule I want and deduce what its properties are. So one of the holy grails of this field is protein folding, right? Lots of bacteria, lots of viruses, human beings ourselves. We can do a lot of really cool things. So if we can design an amino acid sequence and design how that sequence folds into a protein that is a very specific catalysis, or it degrades a toxin or something like that, in theory, we could design a bacteria or we could design a protein that does anything we want it to do. But the problem is, it's really, really, really hard to accurately predict and model the fluid structure. So most all the simulation strategies that we do right now are good guesses, but they're not good enough to get to that level where we could accurately predict protein folding. They're just not that good yet, and they won't be that good for quite some time. Okay, so hope you walk away with a good fundamental understanding of what the radial distribution function is. We're going to continue to talk about it, but internalize this concept. It is extremely important moving forward. See you Friday.